Okay, welcome everybody. I'm Tom Viner. I will be telling you about two types of testing. Property-based testing, fuzzing, which I'm calling tongue-in-cheek to failure-seeking missiles. So I'm here to challenge how you test your code. As an audience starting off point, let's just see, most of you will have written unit tests. Who has only used hard-coded input values in your unit tests? Okay, most people. And who's used some form of random data? Okay, so not quite as many, but plenty of people. So I'm here to ask you, are you testing your code hard enough? Are you stretching it? Are you asking it questions it wasn't expecting? Are you an aggressive interviewer, or are you a softball interviewer who asks easy questions? So this was a question she wasn't expecting, so this is what we're trying to do with your code. So what are we trying to achieve with our test input data? Possible goals would be, most obviously, covering the happy path. Does it have the features that we were intending it to have? That would be an absolute minimum. What about covering the validation steps where the validation fails, or exception handling where something a bit different has occurred? Okay. But what about the exceptions you weren't expecting? I guess by definition you can't write a test for that because you weren't expecting it. And then we can also think about path coverage, so not just lines covered, but actual paths taken through the code base. And this will come up again a bit later. So I'd like to give you a moment just to, with this green square here, think about your own testing, your own examples of data you have in your tests, and which type of points do you pick? Do you pick bob@example.com, or do you try and pick something a bit more tricky? So would you take an adversarial approach or a kind of softball approach? This is an artist's impression of picking all the easy examples, missing the edge cases. So for example, do you use ASCII or do you put in a Unicode snowman? Would you have an empty list as well as a list with things in it, an empty string, large or negative or floating point numbers, as in trying to trip up your code? So what are the ways we can use to create test data? As the little survey there covered, hard-coded values. You could just import random and pick any old integer between 1 and 1,000,000. And that's actually what Model Mummy does. It just tries to give you random data when you use it with Django. Or maybe you could fire a failure-seeking missile at your code. Let's take a closer look. So QuickCheck. Who's heard of QuickCheck? It's a Haskell library. Fair few people. So this is property-based testing. You specify a property of your code, and QuickCheck will quickly check if it can prove you wrong, doing its best to find a counterexample. So this is some Haskell. This is a little example about reversing lists of integers and finding out whether they are the same. So it's saying, imagine you've got 4 integers here, 4 interfingers here, flipping like that versus flipping like that, and put them together. Okay? But this isn't Pi Haskell Monad Con, so let's not accidentally learn Haskell. Instead, just by the way, this is what functional programmers think of imperative programming. Anything could happen, according to them, including your dog getting kidnapped. So that's fine. We like Python. So let's delve into the kidnap dog world of Python, which is Hypothesis. This is a Python implementation of QuickCheck, and it also expands beyond QuickCheck a little bit. Written by David McIver, who is sitting in the front row here. So just to remind you, this is the Haskell proposition we had earlier. Let's rewrite that. So we need a little helper function that knows how to reverse a list in Python and give you a list back. So we've written a test, but it takes 2 arguments, which are the 2 lists of integers. The decorator here says, for the first argument, give me a list of integers, and same for the second argument. The assertion is similar that you'd see in any unit test, and we're using PyTest as the runner here, so we can just use the plain assert statement. This is the result. So actually, it's found a counterexample. The proposition was a bit dubious, and just a 0 in the first list and a 1 in the second list fails the proposition. And we didn't have to think up any example data to send into our code. So that's the key point. So what's going on there? How did it find that counterexample? How could it be working? So maybe it's doing a formal proof. There's some sort of automated theorem prover about reversing lists, and it's kind of can work out the answer no matter what I get. If I do these series of operations, I can assert something about the result. No. Luckily for all the mathematicians, the state of formal theorem provers is still pretty not very comprehensive, let's say. They're still arguing about whether 0.5 equals 1 over 2. So no, it's not like that. How else could it be doing it? So I give the secret away. It's actually firing a crud ton of examples at your code, and which is known as fuzzing. So let's actually just have a look at that. So this is the first set of data that Hypothesis sent into our test. I'm going to have to scroll here because there's so many integers. But this false... I'm scrolling the wrong thing. That's going to help. So there's two lists of integers here. And then underneath, you can see it says false, so the proposition is already false. And as I scroll down here, it's running the test again with another list. The first list is getting shorter. First list is getting shorter. One integer, just a 0, and it's going to make the second one shorter, 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 till it gets down to here. And actually it overshoots, and it turns out the proposition's true for this, but it was trying to prove it false, so it keeps on going. Try to simplify it, and it ends up with what we saw here, the simplest possible counterexample that it can find to prove your proposition wrong. And you can actually copy that example and hard code it into your unit tests. If you want your unit test to be deterministic, you could take that and you could say, actually, I'm going to keep that for later. As an aside, if you run the test again, Hypothesis has a database of examples that it's found, so it won't go through the whole long, I'm really trying to trip you up exercise. It will just start with what it had before, try and optimize it. Actually, it can't optimize it, and it will just give you what you had before. Yeah, same as before. So as an overview, what's happening, it's generating, I guess we call it randomesque data, and we'll see a bit more about that in a second. It's running the test repeatedly, so this is a key difference between normal unit testing and hypothesis testing. Your actual test function is getting run many, many times with different inputs instead of you having hard-coded them. If it finds a counterexample, it will shrink it as best it can so that it can be manageable to you as a mere human being. And OK, so is the data really random? Where did all those integers come from? So just to remind you, this is the decorator we had. And actually, David told me that it doesn't show you the strategies involved here. But he can confirm that the strategies are still devious plans to break your code. So this is more or less like a QA trying to test your code, trying to pick examples you weren't expecting. If you say you support integers, then I'm going to give you a massive integer or a negative integer or a whole load of data. We had lists of integers, so you can be interested to see. You can parameterize. You can specify you want a list of this size or that size. And these are probability distributions. So the list has a probability distribution of what size you're going to get, and the integers, again, have a probability distribution of being between this value and this value. And there's two different strategies there, which are different probability distributions. So let's look at another example. This is a tweet that Raymond Hettinger, core Python developer, put out. So I saw that and I thought, well, he's specifying some properties of Python here. I know how to test properties. So let's have a go. He said you take two integers. OK, so I've got two integer strategies there. So this is where the feedback part comes in with the assume function here. You assume something about your data. If it gets down to that point, it's going to quit the test. It doesn't fail it. It just says, you didn't want that. OK, well, I'll try to give you some more data that doesn't doesn't fail your assumption. So this is the kind of failure-seeking element here. When we run it, it passed. OK, I should know better than doubting Raymond Hettinger, but I can and will property test his tweets. So how does it do it? As I was saying, probability distributions, guided feedback via assume, shrinking of counterexamples to a more manageable level that you can actually comprehend them and copy and paste them if you want to, and a database of failing examples so that although things take longer, because you might be running a test 200 times, at least when you hit something interesting, it's going to keep that around, at least on your local machine, so you don't have to spend the time finding that all over again. The internals are very interesting. There's a good blog post about the templating that goes on to produce the input values, which if you're interested, I think you might find quite fascinating, but I won't go into more detail here. So one more strategy, just to have a little look at floating point numbers. I guess they're a bit more complex as an idea, so there's all these different strategies that go into making floating points when you ask for some, including the nasty ones that David showed off in his talk, minus positive infinity, nan, and all that. So it really is trying to trip you up. And I should say it covers all the built-in data types of Python, like lists, sets, strings, whatever. And it can also do recursive data structures now as well. Advanced features. So if you have a data type that's not a built-in Python data type, you can make your own strategies, and you can build them on top of, you can layer them up. So it might be kind of, you take two integers, you do something with them, they come out, they make something else. There's plugins for Django, so it can read the data types from your models, keep things dry. Similarly with NumPy, there's a prototype plugin. And stateful testing, I think this is really interesting. So if you imagine a kind of ASCII adventure where you can go north, you can go west, you can go east, if you have a code base where there's a number of options at each point, you can say to hypothesis, actually kind of navigate through my, through my maze or through my system, and see if you can break it. Okay, so now we're going to look at something else that's been getting a lot of attention recently. How long left? Okay, so who's heard of American Fuzzy Lop? A few people. So I'm going to call it AFL just for brevity. I think Michael Zalewski likes rabbits because his previous fuzzer was called Bunny the Fuzzer, and American Fuzzy Lob is actually a type of rabbit. I guess it's a fuzzy type of rabbit. So fuzzing specializes in security and binary formats. So it's a bit more low level than what we're looking at with hypothesis. We'll get onto Python in a minute, but this is kind of thinking at the C level at this point. So fuzz testing, as I hinted earlier, is about firing data into your program, attempting to crash it. So in this area, we're kind of thinking about crashing our code, finding memory leaks, rather than asserting that properties are true or false. In this workflow, you're going to be leaving things running for a long time. You've got a lot of ground to cover. So the speed of the machines you've got, the number of machines is very important. So fuzzing has been around for a good long while. An example, traditional fuzzer would be Zuff, which is fuzz backwards. And then AFL has a few extra tricks up its sleeve. So just on traditional fuzzing for a moment, Google had a security team that found 1,000 bugs in FFmpeg, which, as you may know, is a popular image library. This is slightly terrifying. They did have up to 2,000 cores for 2 years. Okay, so like I said, a lot of ground to cover. But, a lot of these bugs were things that could be easily, well, not easily, but exploited. Well, actually, it does say easily. So 100 to 200 zero-day exploits here. I was talking to one of the FFmpeg developers at EuroPython, and he said he wasn't particularly surprised, and he didn't think the code base was bad or worse, a lot worse than any other code base, but they're doing a lot of binary operations. It's very hard to avoid memory leaks and problems like that. So these are kind of part of the course, but tools like this help find at least some of the bugs involved. So AFL is a traditional fuzzer in that it has to be fast and reliable and simple to configure. It does input mutation, so it takes some sample inputs, splices them together, mashes them up, does some bit flips, byte flips, things like that. But it also has an extra trick, which is compile time instrumentation. So this means that when it gives a certain input, it knows the path through your code base that the code takes. So it gives you a different input, it takes a different path. Maybe another input takes the same path. That's not so interesting. It will throw that away. So if it's got a few inputs, it can then splice them together. Maybe that will get somewhere further. And it's trying to map out paths through your code base. And you can see this is getting greater code coverage, but also, like we said earlier, with cyclomatic complexity, it's taking different paths through the code, not just hitting certain lines in the code base. So just very quickly, how you would use this. So if you wanted to compile a C program, you would just do this, but without the AFL bit at the beginning. So that's what I mean by drop-in replacement. So this makes a binary executable with the instrumentation that informs it where in the code base things happen. This is how you run it. So instead of just running your binary, you run AFL fuzz. You give it a small sample of example data. It doesn't have to be, a great corpus or anything, but it will take what you give it, splice it up, mix it up, and try to come out with something interesting. And when it randomly hits something interesting, it will know it got a bit further in the code base. This is the dashboard you see when you run it. So I'll point your eyes in a particular couple of directions because there's a lot going on there. So total paths in the top right. So this, if you want to see the longer version of this talk, by the way, it was at EuroPython. You can see the code this was running. So there was 4 paths, and we can see on the top right, it actually located the 4 paths and the one path that caused the crash. Down in the bottom left, you can see the fuzzing strategies. So it's doing bit flips, byte flips. It's causing havoc. You can give it a dictionary of terms to help it along if it's not really going to guess things like SQL commands, things like that. And in 2.5 minutes, it's done almost 1 million runs of the code. So that's the kind of speed we're talking about. This is a list of the bugs it's found. Actually, I could only fit a third on the slide. But yeah, it's very impressive. I think it's going to continue to be finding a lot of bugs for a while to come. So as I say, it's a traditional fuzzer, but with this extra secret weapon. And it uses genetic algorithms for mashing the examples together and finding interesting examples that progress further in the code base and maybe reach the points that are going to blow up. So Python AFL, to move one level up, is a Python wrapper. It uses Cython. It uses sys.setTrace to know which part of your Python code base you're in at any moment. It has to convert your Python exceptions into signals because that's what AFL looks for. And you run it like this, which is essentially similar to what we had before, but with the pi at the beginning. Alex Gaynor was using this to look for security problems in the cryptography library and actually did find a number of examples they hadn't considered and bugs in his own library and in the upstream library that he uses. So moving on to conclusions, what are the interesting questions raised here? So we're talking about randomness. That means that things are not reproducible. Something different might happen next time you run your tests. That causes a problem for some people because if their test suddenly fails, they want to know that it was the latest patch that made it fail because they tested all the previous patches. So that's one viewpoint. Consistent pass or fail that's always going to be true for a given version of the code base. On the other hand, if you keep on running hypothesis tests, you might find more bugs. So that's good too, right? If you want to take a compromise approach, maybe you're running something like hypothesis regularly, and when it finds new bugs, you copy them and you paste them into your deterministic test pack. If you ask David, he'll just say, don't bother with that, just run hypothesis the whole time. It will find more bugs the more times you run it, and stop complaining. No, he might not say that, but you get the idea. So thinking about random data, purely random data is too naive. It's not even going to get in the starting gate. Enumerating all the possibilities just takes too long. Mutating examples that get, say, halfway may help them get a little bit further. And if you've got secret weapon like instrumentation or the assume function in hypothesis. That's going to guide you, and you're going to get a bit further and maybe find the bugs. Which one of these tools should you use? So in general, unit tests should be fast, but they should use adversarial data. Hypothesis can help you do this if your inputs are Python data structures. Something like AFL, Python AFL is more relevant if your inputs are binary. In conclusion, we've seen the two styles of testing, and I think we can agree humans are bad at picking random examples, developers are bad at being adversarial to their own code base, which they love. Computers are fast, so let them break your code, and find more bugs before your customer or your secret service does so. Let me end by saying, don't interrogate your code like a fluffy bunny stuck up a tree. Fire a guided missile to blow branches off the tree and clear up the mess. It's not just me saying it. Celebrity endorsement. I've been Tom Viner. Thank you very much. Any questions? Do you have a microphone? A couple more over here. Someone mind we found a bug.
So, given the existence of hypothesis, if you're just writing standard unit tests, do you think it's still necessary to be adversarial in your unit testing when you could have hypothesis be adversarial for you? Yeah,
well, that's the point. Yeah, I mean, you can attempt to write adversarial, hard-coded examples, but I think the suggestion is that hypothesis may do a better job than you.
So, I mean, you would say that we should still write normal unit tests too, though, right? Ah, yes, okay, fair enough. Okay, thank you.
I mean, you should write hard-coded examples if you think something like hypothesis won't cover that ground, or you should help it to cover that ground if you've got specific inputs which might cause a problem. And you can make strategies to help you do that.
I'll talk to you about
okay,
it later.
sure.
I've got a particular
okay.
what units that should be like.
More questions? Anyone else? Cool, thank you.